Have you ever stopped to really think about the invisible forces shaping our modern world? You know, the ones powering everything from your morning coffee maker to the complex algorithms that recommend your next favorite show. It all stems from one incredibly fascinating field: computer science. It's a discipline that underpins nearly everything we do, yet its foundational concepts, what we call its big ideas, can sometimes feel a bit mysterious, almost like, well, hidden magic. But today, we're pulling back the curtain. Our mission on this deep dive is to unravel those truly foundational concepts and pivotal insights that underpin this incredibly vast and impactful discipline. Our goal for you, the listener, is to provide a shortcut to being truly well-informed about the very core of computing. We want to transform what might seem like overwhelming information into, surprising insights and those deeply satisfying moments. We've got a comprehensive overview of computer science fundamentals as our source material, and we're going to extract the most important nuggets, distill the essence, and really bring it to life. So settle in, let's unpack this incredible journey through the landscape of computer science, starting right at the very beginning. It's theoretical bedrock. When we talk about the theoretical bedrock of computer science, we're really diving into the philosophical and mathematical origins. It's about asking, fundamentally, what are computers and what are their ultimate capabilities and limitations? This isn't just abstract thinking, is it? It actually defines the very nature of computation we encounter every day.
It absolutely does, yeah. At the very core of this theoretical foundation are two intertwined fields: computability theory and complexity theory. These disciplines set the boundaries, kind of exploring the fundamental limits of what computers can and cannot do, and then, for the problems they can solve, how efficiently they can solve them.
That makes sense. Okay, let's start with computability theory. It's about answering the question, what can be solved? Who were the pioneers who first grappled with this really profound question?
We have to begin with two brilliant mathematicians working independently in the 1930s, Alan Turing and Alonzo Church. They were wrestling with what it truly means to be a computable function or an algorithm, that precise step-by-step procedure. Turing, in particular, introduced the abstract concept of a Turing machine back in 1936.
The Turing machine, right, I've heard that term before. It sounds incredibly complex, but from what I understand, it's deceptively simple in its core idea, right?
That's a perfect way to put it. Deceptively simple. Imagine an abstract device that reads and writes symbols on an infinitely long tape according to a very simple set of rules. It sounds almost primitive, doesn't it?
Yeah, really basic.
But Turing proved that this abstract machine is what we call universal. Given enough time and memory, a Turing machine can compute anything that any modern computer, from your smartphone to the largest supercomputer, can compute. This wasn't just a theoretical curiosity. It was profound insight that defined the very nature of computation itself. It led to what's known as the Church-Turing thesis, which essentially states that all reasonable models of computation have the same inherent power. This thesis unified our understanding of what an algorithm truly is, regardless of the machine it runs on.
So we've defined what can be computed, but here's where it gets truly mind-bending for me. What about the uncomputable? What are the fundamental limits of these machines, no matter how powerful they become?
This is truly one of the most surprising and dare I say, almost humbling discoveries in theoretical computer science. Turing didn't just show what machines could do. He rigorously proved there are fundamental boundaries, problems that are inherently unsolvable. The classic, most famous example is the halting problem.
Right.
Imagine you want to write a program that can reliably look at any other program and tell you for sure whether that program will eventually finish running or if it will get stuck in an infinite loop forever.
That sounds incredibly useful, almost like a super debugger for all programs. You'd think that's solvable.
Exactly. It sounds intuitively plausible, doesn't it?
Yeah.
But Turing mathematically proved that no such general algorithm can exist. You can't write a universal halting detector. This was a landmark realization, proving that there are certain problems that, no matter how powerful our computers become, they can never universally solve. It showed that the boundaries of computation are not merely about engineering limits. They are inherent mathematical limits.
Wow, that's a powerful insight. So, okay, beyond can it be solved, the next crucial question is how efficiently? This brings us to computational complexity theory.
That's the practical side of the theoretical coin, exactly. It's not enough to simply solve a problem. We need to solve it efficiently. In terms of the time it takes and the memory resources it consumes, you can imagine there's a dramatic difference in difficulty, even among solvable tasks.
Oh, definitely. Some problems just feel harder, even if you know they can be solved eventually.
Precisely. So in the mid-20th century, computer scientists began categorizing problems into complexity classes, like P and NP. This classification is based on how the required resources, primarily time, scale, as the input size grows. This is where the famous P versus NP problem comes in.
Ah, the million-dollar
The
question.
million-dollar question, literally. It remains one of computer science's greatest unsolved puzzles. It asks, is it true that any problem whose solution can be verified quickly, that's the NP class,
Okay.
can also be solved quickly, that's the P class?
So, if I can quickly check an answer to a problem, does that mean I can also quickly find that answer in the first place? That's the essence of PVS NP. And you mentioned NP complete problems. What are those about?
Yes. Stephen Cook and others in the 1970s identified this set of problems known as NP-complete problems. These are a fascinating group of problems that are, in a sense, equally tough, intractably hard, we suspect. What's truly intriguing is that if you find a fast, efficient solution for one single NP-complete problem, you would instantly have a fast solution for all of them, thousands of seemingly different problems.
Wow, okay.
So for you, the listener, understanding complexity theory is crucial because it helps guide practitioners. It tells them when to really push for optimizing algorithms and when to accept that a problem is probably inherently hard. Sometimes you have to seek alternative approaches, like approximation algorithms or heuristics. It's about knowing the practical feasibility of your computational goals.
That's incredibly insightful. So, from the limits of possibility, we then think about practical efficiency. And there's a third foundational idea that underpins so much of our digital world. Information theory, pioneered by Claude Shannon back in 1948.
Shannon's work is another cornerstone that completely shifted our understanding. He created the mathematical framework for quantifying information itself, like what is information. He showed that all forms of data, whether it's text, images, sound, whatever, can ultimately be represented as discrete units, specifically as bits, zeros, and ones. His work also established fundamental mathematical limits, like the famous Shannon limit for error-correcting codes.
Okay.
This defines how efficiently information can be encoded and transmitted without errors, even over a noisy channel like a crackly phone line or wireless signal.
This sounds like the invisible backbone for so much of our digital lives. Data compression, error correction.
It truly is. Information theory underpins data compression, allowing us to, send large files efficiently over the internet. It underpins error correction, which ensures your phone call or streamed video remains clear despite network interference. And it underpins cryptography, which we'll definitely discuss later. It transformed information from a vague concept into a rigorous, quantifiable mathematical discipline.
So, with these fundamental questions of what can be done and how efficiently shaping our theoretical understanding, let's now dive into the practical recipes and structures that actually turn these theories into working systems.
Right. Building directly from those theoretical foundations, we arrive at the concrete tools that computer scientists use every single day: algorithms and data structures. Think of an algorithm as a precise step-by-step recipe for solving a problem. Like baking a cake, you follow the instructions. And a data structure, that's the organized way you arrange your ingredients on the counter or in the pantry. Together, they form the art and science of problem-solving in computing.
So it's not just about having the right steps, but also deliberately organizing your ingredients, your data. I know Donald Knuth's multi-volume The Art of Computer Programming is legendary in this space for really systematizing their study.
It absolutely is a foundational text. And a pivotal insight here, one that often surprises people, is that choosing the right data structure can simplify a problem dramatically. It can make algorithms vastly more efficient. It's all about the power of organization. Imagine you're trying to find a specific book in a library. If all the books are just piled randomly on the floor, well, good luck.
Yeah, that would be chaos. A linear search, right? Checking every single book.
Exactly. You might spend hours checking every single one. That's a linear search. But if that library has a precise cataloging system organized by genre, author, title,
You can find it much faster.
you can locate your book in minutes. The aha moment is realizing that how you organize the information can matter even more than how fast you can physically, say, walk down an aisle.
That's a fantastic analogy. Can you give us a concrete example of this efficiency in practice, maybe comparing different data structures?
Certainly. Let's consider some classic data structures.
Right.
Arrays, linked lists, stacks, queues, trees, graphs, hash tables. Each has different strengths and weaknesses depending on the task. For instance, when searching for an item, if it's just in a simple unsorted list or array, in the worst case, you might have to check every single item. We describe this using big O notation as ON, meaning the time it takes grows linearly with the number of items in. So a million items could mean a million checks, potentially.
Which gets slow very quickly.
Very quickly. But if that data is organized into something like a balanced binary search tree,
Okay, what does that do?
well, a balanced tree structure allows you to dramatically speed up the search. Each step in your search can effectively eliminate half of the remaining possibilities. So to find something in a list of a million items, instead of potentially a million checks, you might only need around 20 checks.
Wow, 20 versus a million. That's a huge difference.
It's enormous. That's O log n, logarithmic time. It's incredibly efficient for fast lookups, especially when you're dealing with large data sets. This profound difference in performance really highlights why choosing the right data representation is so crucial for building efficient real-world applications.
So the structure truly matters just as much as the steps. Okay, what about the greatest hits of algorithmic design paradigms? The actual recipes that solve common computational problems?
Right. We have established families of algorithms that illustrate powerful design approaches. Take sorting algorithms, for example, things like quicksort, merge sort, heap sort. They teach us the divide and conquer approach.
Divide and conquer.
Yeah, it means breaking down a big problem into smaller, more manageable subproblems, solving those smaller problems recursively, and then combining the results. This approach often leads to optimal efficiency. Then there are graph algorithms. These are absolutely essential for problems involving networks and relationships.
Like what? Social networks? Maps?
Exactly. Finding the shortest paths between two locations for GPS navigation, analyzing network flows in supply chains, understanding connections in social networks, even modeling dependencies in complex projects. Graphs are everywhere.
I've also heard of dynamic programming. What's the core idea there? It sounds a bit intimidating.
Dynamic programming, pioneered by Richard Bellman, is a really powerful technique. It's for solving complex problems by breaking them down into simpler, overlapping subproblems. The crucial part is that you solve each subproblem only once, and then you store its result, usually in a table.
So you don't recalculate things over and over.
Precisely. If you encounter the same subproblem again, you just retrieve the stored answer instead of recomputing it. Think of calculating the Fibonacci sequence efficiently, or finding the shortest path in a weighted graph where paths might overlap. This technique prevents redundant calculations, leading to significant speedups for certain classes of problems. And then we have greedy algorithms.
Greedy, that sounds interesting.
Yeah, the idea is you make the locally optimal choice at each step, hoping it leads to a globally optimal solution for the entire problem. Sometimes it works, sometimes it doesn't, but when it does, it's often very efficient. Huffman coding, which is widely used for data compression, is a classic example of a successful greedy algorithm.
So these aren't just abstract ideas, they're fundamental toolkits with proven performance guarantees that developers use every single day. How do computer scientists rigorously analyze these algorithms to know their true performance, to compare them?
That's where techniques like big O notation become vital. It's a precise mathematical way of quantifying how the running time or memory usage of an algorithm grows as the input size increases. It gives you a concise way to predict how an algorithm will perform with larger and larger inputs, abstracting away constant factors and lower-order terms.
So it focuses on the scaling behavior.
Exactly. We also distinguish between worst-case and average-case analysis to understand performance under different conditions. An algorithm might be fast on average, but terrible in some specific scenarios. For instance, an algorithm proven to run in polynomial time, like O(n)(2) or O(n)(3), is generally considered tractable. It's feasible to solve even for very large inputs. In stark contrast, exponential time algorithms like O(2n) quickly become infeasible as the input grows even modestly. This underscores why we need these analytical tools to choose the right tool for the job.
And you mentioned pioneering figures like Edsger Dijkstra and Tony Hoare earlier. Beyond their specific algorithms, what was their broader impact on how we think about programming?
Oh, huge impact. They were not just influential for specific algorithms like Dijkstra's algorithm for shortest paths or Hoare's quicksorts. They were champions of rigorous, structured programming and algorithmic clarity. Dijkstra, for instance, famously advocated against the unrestricted use of the go-to statement in his 1968 letter, Go-to statement considered harmful.
Right, I've heard of that. It caused quite a stir.
It did. He argued it led to messy, hard-to-understand spaghetti code, pushing instead for code that was logically structured using loops and conditionals, making it easier to reason about and prove correct. Their contributions really solidified programming as a rigorous engineering and scientific discipline, not just a craft or an art form. The development of this kind of algorithmic thinking using abstraction, recursion, rigorous proof is a foundational concept that permeates all of computer science.
So with our smart recipes and organized data, where do these logical instructions actually run? That brings us to the very foundation of computing power, the hardware itself. This is where we focus on the physical machines, the silicon and wires that literally bring computation to life. And the first truly revolutionary idea here seems to be the stored program concept.
Indeed. The stored program concept is, well, it's the profound notion that a computer's instructions, its program, can be stored in the same memory as its data. This might seem utterly obvious to us now, looking back.
Yeah, how else would it work?
Right. But it was a paradigm-shifting idea articulated by John von Neumann in his influential 1945 EDVA report, building on Alan Turing's earlier theoretical work.
And its implication was massive, wasn't it? It transformed what a computer could actually do.
Absolutely monumental. It meant a single machine could easily switch between different programs simply by loading new instructions into memory. No rewiring needed. Even more powerfully, it meant a program could potentially modify its own instructions while running, leading to incredible flexibility. This was a massive leap from earlier machines that were essentially hardwired for specific single tasks. This simple yet powerful von Neumann architecture, consisting of a central processing unit, CPU, memory, and input-output devices, became the universal blueprint for virtually all modern computers. It's this elegance and flexibility that truly transformed what was possible.
And then came the hardware milestones, transforming computers from room-sized behemoths using vacuum tubes, right, into these pocket-sized powerhouses we have today.
Yes. The very early machines like ENIAC and EDSAC in the 1940s used those large, hot, and often unreliable vacuum tubes. Thousands of them. But the true game changer, the invention that enabled everything that followed, was the transistor. Invented in 1947 at Bell Labs by Bardeen, Bratton, and Shockley.
Won them the Nobel Prize.
And rightly so. Transistors are tiny, solid-state electronic switches. They are vastly smaller, faster, consume much less power, and are far more reliable than vacuum tubes. They paved the way for unprecedented miniaturization.
Which then led directly to integrated circuits, putting multiple transistors on one chip.
Exactly. By the late 1950s and 1960s, pioneers like Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor figured out how to put many transistors, and thus entire circuits, onto a single chip of silicon. That's the integrated circuit, or IC. This innovation led directly to the first microprocessors in the early 1970s, like Intel's 4004 in 1971, and then the much more capable 8080.
Putting an entire CPU on one single chip?
An entire CPU on a chip. This incredible miniaturization wasn't just incremental progress. It fueled the exponential growth in computing power that we've witnessed for decades.
And that exponential growth leads us directly to Moore's Law, famously observed by Gordon Moore, co-founder of Intel back in 1965.
Moore's Law is a pivotal observation in hardware history. Moore noticed that the number of transistors that could be affordably placed on an integrated circuit was doubling roughly every year or two. And astonishingly, this trend held, more or less, for well over 50 years. It led to truly incredible exponential growth in computing power and memory capacity.
It's staggering. To put it into perspective for you, the listener, this is precisely why your smartphone today is literally thousands, maybe millions of times more powerful and has vastly more memory than the supercomputers that filled entire rooms just a few decades ago.
That's right. Early mainframes had kilobytes of memory and processed thousands of operations per second. Today, we're talking gigabytes of RAM and billions of operations per second in devices you carry in your pocket. It's a direct consequence of Moore's Law in action.
It's an astounding testament to engineering ingenuity. But beyond just packing more transistors onto a chip, there have been significant architectural innovations within the CPU itself, right? Like cache hierarchies and pipelining.
That's right. Moore's Law provided the raw ingredients, but architects had to get clever too. Modern CPUs are incredibly complex machines, building upon the basic von Neumann blueprint. Cache hierarchies were developed to bridge the speed gap between the incredibly fast CPU and the relatively slower main memory. Caches act as tiny, super-fast temporary storage areas right near the CPU core for frequently used data and instructions. Pipelining allows the CPU to execute instructions in an overlapping fashion, like an assembly line. While one instruction is being fetched, the previous one is being decoded, the one before that is executing, and so on. Multiple instructions are in different stages of processing simultaneously.
Making things much faster overall.
Much faster. And we've also seen the emergence of specialized processing units, most notably graphics processing units, GPUs. Originally designed for graphics, their highly parallel structure turned out to be perfect for massive numerical workloads, driving everything from video games to scientific simulations to training the most advanced AI models today. While these innovations make modern CPUs incredibly complex, often with multiple cores, deep pipelines, sophisticated branch prediction, and concurrent execution capabilities, they still logically implement that elegant stored program model at their core.
And underlying all this intricate hardware is another truly foundational concept: binary logic. The incredible fact that all computing ultimately reduces to manipulating simple zeros and ones, it seems almost too simple.
It does, but it's profoundly powerful. This goes back even further to the 19th century mathematician George Boole, who developed Boolean algebra, a system of logic using only true-false values, or ones and zeros. Then, in the 1930s, Claude Shannon, in his master's thesis, made a brilliant connection. He recognized that electrical circuits, which are either on or off, could perfectly implement this Boolean logic.
So switches could represent true and false.
Exactly. You could build circuits to perform logical operations like AND or OR and not using simple electronic switches. Modern digital circuits are built from billions of tiny transistor switches, which act as these fundamental logic gates and also as memory cells to store bits. For example, the addition of binary numbers at the lowest level is performed by circuits called adders, which are themselves constructed from these very same logic gates.
It's a powerful abstraction, isn't it? The ability to layer these complexities. You're building incredible computational power from such simple, fundamental building blocks.
It's a core principle, maybe the core principle, of computer science and engineering. You treat collections of transistors as logic gates. Then you combine gates to build functional units like adders or memory cells. Then you combine those units to build processors. This principle of layered abstraction is precisely what made designing and reliably building incredibly complex computers feasible, despite the inherent imperfections of physical components. It allows designers to focus on one level of detail at a time, managing complexity without being overwhelmed by the entire system. So with these incredibly powerful machines being built, a new challenge emerged. How do we manage all this sophisticated hardware? How do we make it usable for us, the users, and for the application programmers trying to build software on top of it? That's where operating systems came into play.
Okay, so the operating system, the OS, it acts as the mediator between the raw hardware and the software we actually use. It's often called the master control program, right?
That's a great way to describe it, yeah. The core idea is that an OS abstracts away the intricate, low-level details of the hardware, the disk drives, the memory chips, the network card, and it intelligently manages the computer's resources, providing a stable, secure, and reasonably user-friendly platform for applications to run on. This was a critical conceptual shift that emerged in the 1950s and 1960s as computers became more capable, needing to run multiple programs or serve multiple users simultaneously.
What are the key functions it performs? It sounds like it does a lot of heavy lifting behind the scenes.
It really does. An OS is responsible for some really complex tasks. First, resource management, deciding which program gets CPU time, how much memory it can use, who gets access to the disk, and when. Second, hardware abstraction, providing simpler virtual models of devices. So when you interact with files, you're dealing with an abstraction that hides the messy details of raw disk sectors and tracks. Then there's multitasking, which gives the illusion of many programs running at once by rapidly scheduling tiny time slices of the CPU to different tasks. It's a very convincing illusion on modern systems. Memory management is crucial. It prevents programs from interfering with each other's memory space, which would cause chaos, and can even provide virtual memory using disk space to make it seem like you have more RAM than you physically do. And finally, device management, coordinating input-output operations with everything from printers and keyboards to network cards and USB drives.
So it provides these common services so application developers don't have to reinvent the wheel every single time they want to, say, open a file or send a network message. That makes sense. What was the historical evolution of the OS? How did we get from simple batch processing to what we have today?
Early on, in the 1950s, we saw batch processing systems for big mainframe computers, which basically just ran programs one after another from a queue. Not very interactive. But a major conceptual leap came with time-sharing systems in the 1960s. Systems like MIT CTSS and Multics, and most notably UMX, created in 1969 by Ken Thompson and Dennis Ritchie at Bell Labs.
UNIX has had a tremendous lineage and influence, hasn't it? It feels like the grandparent or great-grandparent of so many modern systems.
It absolutely has. Its elegant, relatively simple design, its hierarchical file system, the familiar structure of folders within folders, its powerful command line shell, and the fact that it was written primarily in the high-level C language.
That made it portable.
Exactly. That portability was a crucial design principle. It made it relatively easy to move Unix to new hardware platforms. Many modern operating systems like Linux, macOS, iOS, Android, they all trace their lineage or carry forward its fundamental design philosophies. Unix really established interactive multi-user computing as a standard utility rather than a specialized luxury.
And within the OS, there are crucial concepts like processes and threads. What exactly are those, and why are they important for how the OS works?
Right. These are abstract units of execution that the OS manages and schedules on the CPU. Think of a process as a running program with its own isolated memory space and resources. Each application you run is typically a separate process. Threads, on the other hand, are smaller units of execution within a single process. Multiple threads in a process share the same memory space, which allows them to communicate and cooperate more easily, but also introduces risks if not managed carefully. The OS is critical for security and reliability here. It enforces protection between processes, preventing one crashing program from bringing down the whole system or accessing another program's sensitive data.
But managing all these things running seemingly at once, concurrency introduces its own set of problems, right? Like race conditions and deadlock, which sound like digital traffic jams.
That's a perfect analogy. Concurrency is powerful but tricky. A race condition occurs when the outcome depends on the unpredictable timing of multiple threads accessing shared data. Deadlock happens when two or more processes are stuck waiting for each other to release resources.
Like two people stuck in a narrow hallway, neither willing to back up.
Precisely. To solve these complex concurrency problems, computer scientists like Dijkstra and Hoare developed crucial synchronization mechanisms, things like mutex locks, mutual exclusion, semaphores, and monitors. These are tools that allow multiple programs or threads to coordinate their access to shared resources safely without corrupting data or getting stuck in deadlock. They are absolutely essential for building reliable concurrent systems.
And it's not just the OS core, right? There's broader system software, too.
Yes. Beyond the core OS kernel, we have broader system software like compilers, which translate high-level code to machine code, device drivers, software that lets the OS talk to specific hardware, and database management systems, which we'll get to. These all embody deep computer science ideas, bridging the gap between the hardware, the algorithms, and the applications. And modern OCs continue to evolve with concepts like virtualization, letting one OS create multiple isolated virtual machines, each running its own OS. This is a cornerstone of cloud computing. And containerization, using tools like Docker, provides lightweight application isolation, making it easier to package and deploy software consistently. So the OS remains this vital mediator, constantly adapting to make increasingly complex machines usable, secure, and manageable for a vast array of applications.
The OS manages the computer, but how do we as humans tell the computer what to do in a way that makes sense to us? That's where human-friendly programming languages and different ways of thinking about problems truly transform our interaction with machines. This feels like a huge leap in usability.
It absolutely was. We've talked about the theoretical limits in the physical hardware, but programming languages are the pivotal insight that truly humanizes the computer. It's about bridging that vast chasm between abstract human thought and the raw, unforgiving binary instructions the machine actually understands. High-level languages let us write software in an abstract, readable form, which can then be translated automatically into low-level machine code.
And the historical breakthrough here, which you mentioned might get overlooked, was the creation of the very first compiler. Grace Hopper, right?
Yes, Grace Hopper, a true pioneer. In 1952, she developed the A0 compiler, a precursor to COBOL. This was a radical idea at the time, the notion that a machine could automate the tedious and error-prone translation from a human-friendly language to machine code. It demonstrated that writing programs in a higher-level way was not only possible, but incredibly beneficial for programmer productivity. It really accelerated the entire field.
That's a huge leap in efficiency. What were some of the big three early languages that truly set the stage for modern software development? They came pretty quickly after that, didn't they?
They did, in the late 1950s. Three major languages emerged, each designed for vastly different purposes, but collectively proving the power of abstraction. First, Fortran, developed in 1957 by John Backus and his team at IBM. It was designed specifically for scientific and engineering computation. It introduced familiar algebraic notation, and, crucially, its compilers could produce very efficient machine code, rivaling handwritten assembly. It became the backbone for scientific computing for decades.
Okay, so Fortran for numbers. What else?
Then there was LISP, created by John McCarthy in 1958. LISP pioneered functional programming concepts and powerful symbol manipulation capabilities. It became absolutely key for early artificial intelligence research, dealing with logic and symbols rather than just numbers. And finally, COBOL from 1959, with significant contributions again from Grace Hopper and others. COBOL was designed specifically for business data processing, payroll, inventory, accounting. It was notable for its English-like syntax, aiming for readability even by managers, though that's debated.
Right.
These three languages, Fortran, Lisp, and COBOL, collectively proved that high-level languages could indeed boost programmer productivity dramatically, and that compilers could produce highly efficient machine code. The floodgates were opened.
So beyond just specific languages, different programming paradigms emerged, fundamentally different ways of conceptualizing and structuring programs, different ways of thinking about solving problems. What are some of the most influential ones?
Yes, these paradigms are fundamental. They shape how we approach programming. The earliest and still very common is procedural programming. You see this in languages like Fortran, C, Pascal. Here, a program is essentially a sequence of instructions, grouped into procedures or subroutines that operate on data stored in variables. It closely mirrors the step-by-step execution model of the underlying von Neumann architecture.
Okay, that seems straightforward. Instructions acting on data.
Then we have object-oriented programming, or OOP. This emerged conceptually in the 1960s with Simula, was really developed in the 70s with Smalltalk, and later popularized massively by languages like C++ and Java in the 80s and 90s. The revolutionary idea in OOP is organizing programs as collections of self-contained objects. Each object encapsulates both data, its attributes, and the behaviors, its methods, that act on that data.
So data and the code that uses it are bundled together.
Exactly. Key concepts are encapsulation, which means hiding the internal data details behind a public interface. Inheritance, allowing you to create new kinds of objects by extending or specializing existing ones. And polymorphism, enabling different objects to be treated interchangeably through a common interface, which allows for great flexibility. Pioneers like Alan Kay, who worked on Smalltalk, envisioned OOP as a way to model computing after interacting real-world objects. This proved incredibly influential for managing the complexity of large software systems.
Okay, so procedural, object-oriented, what else? Functional programming sounds different.
Functional programming offers a starkly different perspective. It treats computation primarily as the evaluation of mathematical functions, with a strong emphasis on avoiding mutable state, that is, data that changes over time. LISP was the first major functional language, and later languages like ML, Haskell, FChav, and Scala refined the concept. The profound insights here include higher-order functions, functions that can take other functions as inputs or produce functions as outputs, and the crucial concept of avoiding side effects.
Side effects, meaning?
A side effect is when a function modifies some state outside its own local scope, like changing a global variable or writing to a file. Functional programming strives to minimize or eliminate these. This makes reasoning about program behavior much easier because a function's output depends only on its inputs. It also offers significant benefits for parallel processing because if there's no shared mutable state, different computations can run concurrently without interfering with each other.
Interesting. And there's also logic programming like Prolog, which sounds quite different again, like you're talking to a logician.
It is quite different. In logic programming, exemplified by Prolog developed in the 1970s, programs are written as sets of logical rules and facts about a domain. Computation then proceeds by asking queries, or goals. You state what the problem is and the relationships between data, not explicitly how to compute the solution step by step. The language implementation uses powerful inference mechanisms like backtracking search to find solutions that satisfy the logical rules. It's often called a declarative approach, in contrast to the imperative style of procedural programming.
I see the progression from direct step-by-step instructions to modeling real-world objects to pure mathematical functions to logical rules. It's like different tool sets for different kinds of thinking. And there's also the theoretical side of defining these languages precisely, right? Syntax and semantics.
Yeah.
Getting the grammar and meaning right.
Absolutely. A significant theoretical contribution alongside the languages themselves was the development of methods for the rigorous definition of language grammar, using formalisms like Backus-Nair form, BNF, which precisely describes the structure, the syntax of a language, and defining the precise meaning, or semantics, of programs using mathematical models. This enabled computer scientists to logically prove properties about programs like proving a sorting algorithm actually sorts correctly. This led eventually to the field of formal verification, where you use mathematical techniques to ensure programs meet their specifications. This is absolutely crucial for safety-critical systems. Think aircraft flight control, medical devices, nuclear systems where software failure is unacceptable.
And many famous names pop up when we talk about programming languages. These individuals have truly shaped how we build software today, creating the tools we use.
Indeed. Beyond the early pioneers, Edsger Dijkstra, whom we mentioned for algorithms, was hugely influential for his advocacy of structured programming and formal methods, pushing for clarity and provable correctness in code. Nicolaus Wirth designed Pascal in 1970, which became a widely used teaching language specifically because it promoted structured programming and good data structuring practices. He later designed Modula 2 and Oberon, continuing that philosophy. Dennis Ritchie created C in the early 1970s at Bell Labs alongside Ken Thompson, who was developing UNX. C is this powerful, efficient, relatively simple, low-level, high-level language. It gives programmers a lot of control close to the hardware, but with high-level structures. It became hugely influential, especially for systems programming. As we said, UNX was written almost entirely in C.
And C++ and Java are, in a way, its descendants, building on that C legacy but adding new ideas.
Yes, exactly. Bjorn Stroustrup added object-oriented features to C to create C++ in the 1980s, aiming to manage the complexity of larger systems while retaining C's efficiency. It became dominant for large application and systems development. James Gosling led the creation of Java at Sun Microsystems in 1995, with a major focus on platform independence, write once, run anywhere, via its virtual machine, automatic memory management, garbage collection, and features aimed at enterprise applications and the nascent World Wide Web. And simultaneously, more academic or research-focused languages like ML, led by Robin Milner and later Haskell, pushed advancements in robust type systems and purely functional approaches.
Type systems, you mentioned that. What's the big idea there? Why are types so important?
Type systems are a really fundamental concept for writing reliable software. A type system classifies data into different categories like integer, floating point number, string of text, list of customers. By checking types before the program runs, at compile time, the compiler can catch a huge range of potential errors automatically, like trying to add a number to a customer's name. Stronger type systems allow programmers to express more sophisticated invariants or guarantees about their data, leading to more robust and maintainable programs. So the overarching insight across all these languages and paradigms is the language you use profoundly influences how you think about and solve problems. New languages and new paradigms continually emerge to open up more powerful ways of tackling complexity and software development. And, as programs grew from hundreds of lines of code to thousands, then millions, then tens of millions, simply writing code, even with good languages, wasn't enough. We needed a systematic, disciplined way to build and manage these massive software systems reliably. That's precisely where software engineering steps in.
Right. This is where we address the immense challenge of human complexity in software development. I remember reading Fred Brooks's famous 1986 essay, No Silver Bullet. His point was that software complexity is inherent, essential, not just accidental. It's not something you can easily wish away with a single breakthrough tool or technique.
Precisely. Brooks argued that the hardest part of building software isn't the coding itself, but managing the conceptual complexity, figuring out exactly what needs to be built, ensuring all the pieces fit together correctly, coordinating large teams. Software engineering emerged as the discipline dedicated to the systematic, methodical design, development, testing, and maintenance of large, reliable software systems. It directly tackles the fact that software development is often limited more by human factors, managing large teams, ensuring clear communication, making consistent design decisions over long periods than by raw hardware limitations. It's about bringing engineering discipline to the sometimes chaotic art of programming.
So what are the key principles, the big ideas that software engineering uses for taming this kind of complexity? How do we manage these huge projects?
Several foundational ideas emerged as crucial. First, abstraction. We've seen this before, but it's key here too. Hiding lower-level implementation details behind simpler, higher-level interfaces. For example, when you use a library function like sort array, you don't need to know the intricate details of whether it uses quicksort or merge sort internally. The extraction is simply that it sorts the array correctly and efficiently. Second, and hugely important for large systems, is modularity and information hiding. This means breaking complex systems into smaller, independent components or modules, each with well-defined responsibilities and clearly specified interfaces for how they interact with other modules.
Okay, breaking it down into manageable chunks.
Exactly. David Parnas, in a highly influential 1972 paper, famously emphasized that modules should hide their internal design decisions. like the specific data structure used inside, exposing only what's absolutely necessary through their interface. The benefit: independent teams can work on different modules simultaneously, and you can update or completely change the internals of one module without breaking other parts of the system, as long as you maintain the agreed-upon interface. This is critical for long-term maintenance and evolution. Third is hierarchical design, structuring systems in layers, from high-level architectural overviews down to low-level implementation details, providing clear map of the system's overall structure and how components relate.
And the development methodologies themselves have evolved too, haven't they? From the more rigid waterfall model to the flexible, agile approaches that seem so prevalent today.
Exactly. The early waterfall model, with its distinct sequential phases of requirements design, implementation, testing, maintenance, provided structure, but was often too rigid. It assumed you could perfectly define everything up front and that requirements wouldn't change.
Which rarely happens in the real world.
Almost never on complex projects. In response, agile methodologies, like Scrum or Kanban, gained prominence starting in the late 1990s and early 2000s. Agile emphasizes iterative development, building the software in small, incremental cycles, continuous customer feedback, collaboration, and flexibility in adapting to changing requirements throughout the project lifecycle. The key idea is continuous refinement and adaptation, embracing change as a normal part of development rather than trying to fight it with a single, upfront, big design that might become obsolete before the project is even finished.
What about enabling technologies and practices that support this systematic approach to software quality? Things developers use day to day.
Or several are absolutely essential now. Version control systems like Git, which is ubiquitous today, are fundamental for collaboration. They allow multiple developers to work on the same code base, track every single change, merge contributions, and easily revert to previous versions if needed. It's hard to imagine large-scale development without them.
Right, managing the history of the code.
Exactly. Then there are practices like code review, where developers examine each other's code to find defects, suggest improvements, and share knowledge. Unit testing, where developers write small, automated tests for individual pieces of code, functions or methods, to ensure they work correctly in isolation. And continuous integration, CI, where code changes from all developers are frequently merged into a central repository and automatically built and tested. These practices reflect the idea that software quality must be systematically controlled and built in from the very beginning, not just checked for at the end before release.
And there's a whole field of design patterns and architectural patterns that help codify good solutions to common problems, right? Kind of like blueprints.
Yes, that's a great analogy. The design patterns movement, famously popularized by the Gang of Four book in 1994, cataloged common recurring solutions to specific software design problems within object-oriented programming. Think of patterns like singleton, ensuring only one instance of a particular class exists, observer, allowing objects to notify others automatically when their state changes, or factory, providing a standard way to create objects. These patterns provide a shared vocabulary and reusable blueprints for developers.
So you don't have to reinvent the wheel for common situations.
Exactly. And at a higher level, architectural patterns, like client-server, model view controller, or MVC, microservices, event-driven architecture, provide templates for structuring entire systems, guiding how different major components interact and how data flows through the system.
And Margaret Hamilton, who famously led the Apollo project's onboard flight software team, actually coined the term software engineering herself to emphasize this need for rigor and discipline, didn't she?
Her contribution was absolutely pivotal, yes. She led the team that developed the incredibly complex software for the Apollo guidance computer. And its success, the fact that this mission-critical software, with millions of lines of assembly code equivalent, had essentially no critical bugs during the moon landings, was a landmark achievement. It proved that careful design, exhaustive testing, they thought of everything, meticulous configuration management, and disciplined engineering practices could yield highly reliable software, even for incredibly complex and safety-critical missions where failure was not an option. She deliberately used the term software engineering to gain legitimacy for the field, arguing it needed the same kind of rigor and discipline as other established engineering fields like building bridges or rockets. So in conclusion, software engineering manages this inherent complexity through discipline by using abstraction, modular design, rigorous processes, proven patterns, and robust tools, enabling us to create reliable software systems far beyond what any single person could comprehend in full detail.
Okay. From mastering individual programs to building these vast engineered systems, the next logical step seems to have been connecting computers to each other. This led to a profound shift in how we interact with information and, indeed, with each other. That brings us to computer networks and the internet. The core insight here was this vision of connecting multiple computers for communication and resource sharing, moving beyond isolated standalone machines. This was truly a transformative vision early on.
It was, and it started quite early. Visionaries like J.C.R. Licklider in the 1960s were writing about an intergalactic computer network, imagining a future where information and programs could be accessed from anywhere. This ambitious dream began to take concrete shape with ARPANET in 1969, funded by the U.S. Department of Defense's Advanced Research Projects Agency, ARPA, later DARPA.
ARPANET was a breakthrough because of its use of packet switching, wasn't it? That sounds like a simple but incredibly powerful idea compared to traditional phone networks.
It was a fundamental architectural shift, absolutely key to the Internet's success. Instead of dedicated communication lines, like in the old phone system where a circuit is open for the duration of a call, data in ARPANET was broken into small, independently addressed chunks called packets. Each packet contained destination information and was routed independently through the network, hopping from router to router until it reached its destination. Packets from many different conversations could share the same network links.
What was the advantage of doing it that way?
Two huge advantages.
Okay.
First, efficiency. Network links weren't tied up by a single conversation. They could be shared dynamically, making much better use of bandwidth. Second, robustness. Because packets could be routed independently, if one part of the network failed, packets could simply be rerouted around the damage. The network could heal itself, in a sense. This concept was developed by pioneers like Paul Barron, Donald Davies, and Leonard Kleinrock. You can imagine an early ARPANET map from the 1970s, just a few dozen interconnected nodes at universities and research sites, but it laid the conceptual groundwork for the global network we have today.
And the ultimate challenge, then, was interconnecting different types of networks, not just nodes on ARPANET. That's where the internet truly took shape and became a global phenomenon, right? The network of networks.
Yes, the term internetwork is literally where internet comes from.
Mm-hmm.
The pivotal moment came in 1974 when Vint Cerf and Bob Kahn published the design of TCP/IP, the Transmission Control Protocol, and Internet Protocol. This pair of protocols provided a universal language, a standard way for diverse, disparate networks around the world, university networks, government networks, eventually commercial networks, to interconnect and exchange packets reliably.
So TCP handles reliability, IP handles addressing and routing.
Essentially, yes. IP, Internet Protocol, handles the addressing of packets and routing them across different networks towards their destination. TCP, Transmission Control Protocol, runs on top of IP and provides reliable, ordered delivery of data, handling things like lost packets, retransmissions, and putting packets back in the correct order. This open, modular, layered architecture of TCP/IP was crucial. It allowed the internet to grow organically and explode in size during the 1980s and 90s, becoming the decentralized, scalable, and remarkably resilient global system we rely on today. No single entity owned or controlled it.
And what were some of the killer apps and protocols that truly highlighted the power of this new connected world and drove its adoption?
Well, email, using protocols like SMTP, Simple Mail Transfer Protocol, was one of the very first killer apps back in the 1970s on ARPANET. It fundamentally changed how academics and researchers collaborated across distances. But then, the real explosion in public use came between 1989 and 1991, when Tim Berners-Lee at CERN, the European Particle Physics Lab, invented the World Wide Web.
HTTP, HTML, URLs, all that stuff.
I like all that stuff.
Exactly. He created the system of hyperlinked documents, HTML, the addressing scheme, URLs, the protocol to transfer them, HTTP, and the first web browser and server. This relatively simple system for sharing and linking information graphically, accessed via intuitive web browsers, popularized the internet far beyond academia and government research. It had a truly societal scale impact that's hard to overstate. It put the power of linked information directly into the hands of billions.
What are some key networking principles that allow for this immense complexity with billions of devices to work relatively seamlessly most of the time?
The idea of a protocol stack, or layered architecture, is absolutely fundamental to managing this complexity. Think of the conceptual OSI model, or the simpler, practical Internet Protocol stack, often called the TCP/IP model. Each layer handles specific aspects of communication, building upon the services provided by the layer below it. For example, the physical layer deals with transmitting raw bits over wires or radio waves. The data link layer handles communication between adjacent devices, like Ethernet or Wi-Fi. The network layer handles routing packets across the internet, IP. The transport layer provides end-to-end connections, TCP or UDP. And the application layer supports specific services like the web, HTTP, email, SMTP, or file transfer, FTP.
So it's like building blocks. Each layer only needs to know how to talk to the layers immediately above and below it.
Precisely. This layering is a powerful abstraction because it allows innovation to happen independently at different layers. You can invent new Wi-Fi standards, data link layer, or a new video streaming protocol application layer without breaking the underlying IP network layer, for instance. It promotes modularity and interoperability. Another crucial concept, especially for the services running on the internet, is distributed systems. This is where components of a system reside on different networks' computers and coordinate their actions by passing messages.
Which introduces a whole new set of challenges compared to a single computer.
Oh yes, significant challenges like ensuring consistency across multiple copies of data distributed across different machines.
Yeah.
Achieving fault tolerance, what happens if one or more machines crash, or the network connection between them breaks. Maintaining security in a fragmented, untrusted environment. Computer scientists discovered fundamental theoretical limits here, like the famous CAP theorem formulated by Eric Brewer around 2000.
CAP theorem: consistency, availability, partition tolerance. You can't have all three.
Exactly. In a distributed data store facing network partitions, where parts of the system can't communicate with each other, you are forced to choose between maintaining perfect consistency, all nodes see the same data at the same time, and maintaining availability. Every request receives a response, even if it's slightly out-of-date data. You have to make trade-offs.
So a banking system would probably choose consistency over availability during a partition.
Definitely. You can't have account balances disagreeing, whereas a social media feed might prioritize availability, showing you slightly stale data rather than an error message. To handle these challenges, sophisticated solutions like consensus algorithms, such as Paxos or Raft, were developed. These allow a group of distributed nodes to agree on a shared state or sequence of operations, even in the presence of failures or network delays. These algorithms form the bedrock of modern, reliable distributed databases and, more recently, blockchain and cryptocurrency networks.
So the internet's open, robust, and scalable design built on these layers and principles is truly one of computer science's greatest engineering feats. And it's still evolving constantly.
It absolutely is. From pioneers like Bob Metcalfe, who co-invented Ethernet for local area networking in the 70s, to the designers of TCP/IP, to the architects of today's massive cloud infrastructure and content delivery networks. The Internet's architecture continues to be a marvel of design and evolution, demonstrating the power of decentralized layered systems to connect billions of people and devices, forming a truly global nervous system. The Internet allowed us to send messages and connect machines around the world, but what about storing and making sense of the vast amounts of information being generated every second? That's where database systems transformed how we manage data, making it not just stored, but accessible, queryable, and truly usable.
Right. The core problem, of course, was efficiently storing, retrieving, and managing large amounts of structured data for organizations. Think customer records, inventory, financial transactions, scientific data. And the solution came in the form of database management systems, or DBMS, software designed specifically for this.
Yes, a DBMS is software that provides reliable, efficient, and convenient access to persistent data. It handles all the hard work of storage, indexing, concurrency control, recovery from failures. And the truly revolutionary idea of this domain, the one that dominated for decades, was the relational model, invented by Edgar F. Codd in 1970 while he was working at IBM Research. This was a profound conceptual shift in how we thought about organizing and querying data.
How is this different from what came before? What made the relational model so revolutionary compared to, say, hierarchical or network databases?
Before Codd, data was often stored in complex, pointer-based hierarchical or network structures. These were often efficient for specific, predefined access paths, but they were very rigid. Querying data in new ways or changing the data structure was incredibly difficult and required rewriting applications. Data was tightly coupled to the programs that used it. Codd, with his background in mathematics, proposed organizing data in simple, intuitive tables, which he called relations, consisting of rows, tuples, and columns, attributes. This tabular structure might seem basic now, but it had deep mathematical foundations in set theory and relational algebra. And crucially, he introduced the idea of a high-level declarative query language, which later evolved into SQL structured query language.
Declarative meaning you say what data you want, not how to get it.
Precisely. With SQL, users could specify the data they wanted using logical conditions, e.g., select name from customers where city equals London, and Balance 1000 without needing to know the low-level physical storage details like which disk blocks to read or which indexes existed. The DBMS itself would figure out the most efficient way to execute that query. That was revolutionary.
That sounds incredibly empowering for users and application developers. It decouples the logic from the physical storage.
It absolutely does. The relational model brought several hugely important principles. Data independence, meaning applications don't need to know how data is physically stored or indexed, making systems much more flexible and easier to evolve over time. And set-based operations, allowing you to query and manipulate potentially millions of records with a single, concise SQL statement. By organizing information into logically linked tables via keys, like a customer ID linking orders to customers, relational databases made it much easier to maintain data consistency and avoid redundancy, which was a massive problem with earlier systems. While initially seen as too theoretical or potentially slow, prototypes like IBM System R and UC Berkeley's Ingraze in the 1970s proved its practicality and performance. By the 1980s, relational databases like IBM DB2, Oracle, Sybase, Informix, and later open-source options like MySQL and PostgreSQL came to dominate the industry for decades.
And databases, especially those handling important transactions like banking or e-commerce, needed to handle integrity and concurrency robustly, right? You can't have multiple users corrupting data when they access it at the same time.
Indeed. That's where the concept of transactions and the ACD properties became absolutely central. ACD stands for atomicity, consistency, isolation, and durability.
Okay, break those down. What do they guarantee?
Atomicity means transactions are all or nothing. Either the entire sequence of operations within a transaction completes successfully, or if anything fails halfway through, like a server crash, all partial changes are rolled back, leaving the database in its original state. Think of transferring money between two accounts. Both the debit and the credit must happen, or neither does. Consistency ensures that a transaction brings the database from one valid state to another, preserving data integrity rules, like account balances never going below zero, perhaps. Isolation means that concurrent transactions behave as if they were executed serially, one after another, even though they might be running interleaved in reality. One transaction doesn't see the partial, uncommitted changes of another. This prevents weird anomalies. And durability guarantees that once a transaction is successfully committed, its changes are permanent and will survive subsequent system failures, like power outages.
Those ACD guarantees sound essential for any system dealing with valuable data. How do databases achieve isolation when many users are active?
They use sophisticated concurrency control techniques. The most common is locking, where a transaction acquires locks on the data it needs to modify, preventing other transactions from interfering until the lock is released. There are different types of locks, shared, exclusive, and different locking levels, row level, page level. Other techniques include optimistic concurrency control and multi-version concurrency control, MVCC. Getting this right without causing excessive waiting or deadlocks is a major challenge.
And databases also automatically optimize queries, don't they? That seems like black magic. How does select from giant Vistas table where condition run fast?
It's a hidden marvel, yes. It's not magic, but very clever engineering based on CS principles. DBMS automatically maintain data structures called indexes, often using B-trees or hash tables on certain columns. These indexes allow the database to quickly locate specific rows based on the values in those columns, much like a book's index lets you jump directly to a page discussing a topic rather than reading the whole book.
So the index avoids scanning the entire table.
Exactly. And a complex component called the query optimizer analyzes an incoming SQL query and considers many possible ways, execution plans, to retrieve the requested data. It uses statistics about the data distribution, knowledge of available indexes, and cost models for different operations, like scanning versus index lookup, different ways to join tables, to choose the plan it predicts will be the most efficient. Again, this highlights that powerful separation of concerns. The user or application developer states what data they want declaratively in SQL, and the database system figures out how to get it efficiently. This saves programmers immense effort and allows database administrators to tune performance by adding or removing indexes without changing application code.
But the world of data has changed dramatically in recent decades, especially with the web generating unbelievable amounts of unstructured or semi-structured data. This led to big data and the emergence of NoSQL databases. How did that shift happen?
Absolutely. The sheer volume, velocity, and variety of data generated by web applications, social media, IoT devices, etc., started to push the limits of traditional relational databases in the late 20th and early 21st centuries, particularly in terms of cost-effective scalability and flexibility. First, Data warehouses and online analytical processing (OLAP) systems emerged, specifically designed for analyzing large volumes of historical data, often using different storage techniques like columnar storage, optimized for complex analytical queries rather than transactional updates. And then, driven by the needs of web-scale giants like Google, Amazon, and Facebook, came the NoSQL movement, often interpreted as not only SQL in the mid to late 2000s.
What was different about NoSQL databases?
They often deliberately relaxed some of the strict ACD guarantees or the rigid relational schema model in favor of other properties, like massive horizontal scalability, running across hundreds or thousands of commodity servers, higher availability, and more flexible data models, like key-value stores, document databases, wide column stores, or graph databases. A crucial idea here is eventual consistency. Instead of guaranteeing that all copies of data across a distributed system are instantly consistent, which can be slow and limit availability, many NoSQL systems provide eventual consistency, meaning that if no new updates arrive, all replicas will eventually converge to the same value. This trade-off is often acceptable for applications like social media feeds or product catalogs, where perfect instant consistency isn't always required. Examples include systems like Dynamo, Amazon, Cassandra, Facebook Apache, MongoDB.
And alongside NoSQL, there was MapReduce for processing huge data sets.
Yes, the MapReduce programming model, published by Google in a hugely influential 2004 paper, provided a simple yet powerful framework for processing massive data sets in parallel across large clusters of commodity machines. It breaks down computation into two main phases: a map step where an operation is applied independently to many chunks of input data, and a reduce step where the results from the map phase are aggregated or summarized. The framework automatically handles distributing the work, managing failures, and moving data around the cluster. This model heavily influenced the open-source Apache Hadoop ecosystem and became the standard way to perform large-scale batch data processing for tasks like indexing the web, analyzing click logs, or running machine learning algorithms on terabytes or petabytes of data. So the foundational insight from database systems is that with the right models, relational or otherwise, query languages, and underlying system software, we can efficiently store, manage, and extract extraordinary value from vast amounts of data, underpinning virtually every aspect of modern commerce, science, and society. Influential figures here include Cod, Michael Stonebreaker, Ingress, Postgres, Jim Gray, Transactions, ACID, and many others who built these powerful systems.
Okay. With vast amounts of data stored and managed effectively, the next logical step, it seems, was to make computers not just process information, but truly understand it, learn from it, reason with it, and even create new things based on it. Welcome to the world of artificial intelligence. Artificial intelligence, or AI. It embodies this long-held aspirational goal of making computers perform tasks that typically require human-like intelligence. We're talking about problem-solving, reasoning, learning, perception, understanding language. It's a really broad field.
It is incredibly broad. The field officially began, or at least got its name, in 1956 at the famous Dartmouth Summer Research Project on Artificial Intelligence. John McCarthy coined the term AI there. He and other pioneers like Marvin Minsky, Alan Newell, and Herbert Simon famously posited that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. A very bold claim back then.
Extremely bold, and it certainly kicked off a lot of excitement. But AI has also had its cycles of, massive optimism followed by periods of disillusionment, often called AI winters, where progress seemed to slow and funding dried up. Why did that happen?
Indeed. The history of AI is marked by these cycles. In the early decades, roughly the 1960s through the 1980s, the dominant approach was symbolic AI, sometimes called good old-fashioned AI, or JUGO-FA. This focused on representing knowledge explicitly using symbols, rules, and logic. Early examples included Newell and Simon's General Problem Solver, which tried to mimic human problem-solving steps, and later Expert Systems in the 80s, which encoded the knowledge and reasoning rules of human experts in specific domains, like medical diagnosis or geological exploration.
And they had some successes, right?
They did, in narrow, well-defined domains, but they ran into limitations. Handcrafting and maintaining the vast, complex sets of rules needed for broader intelligence proved incredibly difficult and brittle. The systems often failed unexpectedly when faced with situations outside their programmed knowledge. This led to those AI winters when the initial hype didn't match reality. So if hand-coding all the rules of intelligence proved too difficult, the focus must have shifted away from programming intelligence directly towards having the machines learn intelligence from data instead. Precisely. This is the core insight behind machine learning, ML, which has become enormously influential. and is the driving force behind the current AI boom we're experiencing. Instead of telling the computer how to be intelligent, you give it data and algorithms that allow it to learn patterns and behaviors from that data. The seeds for ML were planted quite early. Frank Rosenblatt's perceptron in 1957 was a very simple mathematical model of a single neuron that could learn to classify patterns. While its limitations were famously highlighted by Minsky and papered in 1969, leading to a decline in neural network research for a while, the underlying idea persisted. By the 1980s, researchers like Geoffrey Hinton, Jan LeCun, and Yoshua Bengio revived neural networks with the development of the backpropagation algorithm. This provided an efficient way to train networks with multiple layers, allowing them to learn much more complex patterns.
And this research from the 80s and 90s laid the groundwork for the deep learning explosion we've seen in the last decade or so. It feels like it almost came out of nowhere for many people watching from the outside.
It might seem that way, but it was built on decades of steady, often quiet research. Deep learning, essentially, machine learning using neural networks with many layers, deep architectures, truly exploded in the 2010s. This was thanks to two critical enabling factors converging.
What were those?
First, vastly increased computing power, particularly the realization that GPUs, originally designed for graphics, were incredibly well suited for the massive parallel matrix multiplications needed to train deep neural networks. Second, the availability of massive datasets, often labeled, fueled by the internet and digitization, like ImageNet, a huge database of labeled images. A watershed moment came in 2012. A deep convolutional neural network, trained by Hinton's team, dramatically outperformed all other approaches in the prestigious ImageNet Image Recognition Challenge. Its error rate was significantly lower than anything seen before.
And that really kicked things off.
That single event is widely credited with sparking the current wave of intense interest, investment, and breakthroughs in AI across computer vision, speech recognition, natural language processing, and more. It showed the incredible power of deep learning when combined with enough data and compute.
So machine learning is clearly a key subfield of AI, perhaps the dominant one today. What are some of the other important subfields that contribute to this broader goal of creating intelligent machines?
Right, AI is broader than just ML. Machine learning, ML itself, focuses on algorithms that improve their performance on a task through experience or data. This includes various techniques like supervised learning, learning from labeled examples, unsupervised learning, finding patterns in unlabeled data, reinforcement learning, learning through trial and error with rewards, as well as neural networks, decision trees, support vector machines, etc. A central goal in ML is generalization, the ability of a trained model to perform well on new unseen data, not just memorize the training data. Then there's computer vision, which focuses on enabling machines to see and interpret visual information from images or videos. This ranges from basic tasks like edge detection to complex ones like object recognition, scene understanding, and the real-time perception needed for self-driving cars. Convolutional neural networks, CNNs, have revolutionized this field. Natural language processing, NLP, deals with the interaction between computers and human language, understanding text and speech, generating coherent language, translation, sentiment analysis. This field has also been transformed recently by deep learning, particularly by large language models, LLMs, based on the transformer architecture, like the GPT series.
Okay, vision and language. What else?
Robotics marries AI algorithms for planning, decision-making, learning, with physical embodiment sensors to perceive the world and actuators, motors, grippers, to interact with it. It brings AI out of the purely digital realm. Knowledge representation and reasoning, KRR, is closer to the symbolic AI roots. It deals with how to represent facts, rules, and relationships about the world in a way that computers can perform logical inference and reasoning. Think ontologies, logic programming, inference engines. And planning and decision-making focuses specifically on algorithms that allow an AI agent to figure out a sequence of actions to achieve specific goals, often in complex or uncertain environments. Classic examples include search algorithms like A for pathfinding in games or robotics.
There have been some truly landmark milestones over the years that really brought AI into the public consciousness, showing just how far the field had come, often by beating humans at complex games.
Definitely. Those moments capture the imagination. IBM's Deep Blue supercomputer defeating reigning world chess champion Garry Kasparov in 1997 was huge. While Deep Blue relied heavily on brute force calculation using specialized hardware and sophisticated heuristic search algorithms, it was a powerful demonstration of machine capability in a domain previously thought to require deep human intuition. Then, IBM Watson winning the quiz show Jeopardy! In 2011 was another major milestone. This showcased impressive advances in NLP, information retrieval, and the ability to process and synthesize information from vast knowledge bases to answer complex questions posed in natural language. And perhaps most symbolically for the modern AI era, DeepMind's AlphaGo defeating world Go champion Lee Sedol in 2016. Go is vastly more complex than chess, with an enormous search space. AlphaGo used a combination of deep neural networks, trained on human games and through self-play, and Monte Carlo tree search, demonstrating that AI could achieve superhuman performance in highly complex intuitive domains, sometimes discovering strategies humans hadn't conceived of.
Right? Discovering new ways to play the game. And today, AI is applied everywhere, it seems. Medicine, finance, transportation, entertainment. It feels like it's transforming every industry.
It is, from diagnosing diseases in medical images to algorithmic trading in finance to recommendation systems online to powering virtual assistants to enabling self-driving features in cars. And with that widespread application come increasingly urgent discussions around crucial ethical considerations. Things like bias in AI systems trained on biased data, the need for transparency and interpretability of AI decisions, understanding why an AI made a certain recommendation or prediction, ensuring AI systems are trustworthy and robust, and aligning AI goals with human values. These are major research areas now. Foundational thinkers like Alan Turing, who proposed the Turing test for machine intelligence back in 1950, early leaders like McCarthy, Minsky, Newell, and Simon, and more recent influential figures like Hinton, LeCun, Bengio, Andrew Ng, Fei Lai, and many others have shaped this incredibly dynamic and rapidly evolving field. The overarching insight of AI is about making software smart enough to tackle tasks previously requiring human intelligence, with machine learning currently being the dominant approach. It continually blurs the lines with fields like cognitive science, psychology, and neuroscience as we try to both understand and replicate intelligence in machines. So beyond making machines intelligent in an abstract sense, we also want them to communicate with us intuitively, visually, and interactively. This isn't just about functionality. It's about making computers a natural extension of our own senses and abilities. That's precisely where computer graphics and human-computer interaction truly shine. They bridge the gap between the machine's internal state and our human perception.
Okay, so computer graphics is about generating and manipulating visual content using computers, bringing the visual world to life digitally. And Ivan Sutherland's Sketchpad in the 1960s seems like an almost unbelievably early and visionary example here.
It was absolutely groundbreaking. Sutherland's PhD thesis project, Sketchpad, demonstrated the revolutionary idea of interactive, object-oriented graphics on a CRT display using a light pen. It showed that computers could be used not just for calculation, but as a medium for visual creation and manipulation in real time. It anticipated many concepts found in modern computer-aided design, CAD systems, and graphical user interfaces. Over the following decades, the field of computer graphics developed sophisticated mathematical techniques for modeling 3D objects, using representations like polygon meshes, NURBS curves, or subdivision surfaces, and for rendering these scenes realistically.
Rendering meaning.
Yeah.
Creating the final image.
Exactly. Creating the 2D image from the 3D model. This involves simulating how light interacts with surfaces using complex algorithms like ray tracing, which follows the path of light rays from the camera back to light sources, calculating reflections, refractions, and shadows for photorealistic results. Or, more commonly, for real-time applications like games, using faster rasterization techniques. This was all coupled with incredible hardware acceleration through specialized graphics processing units, GPUs. GPUs contain hundreds or thousands of small processing cores designed to perform the parallel calculations needed for graphics, like transforming vertices and shading pixels, incredibly quickly.
And the results of all this graphics work are absolutely everywhere today, aren't they? From the graphical user interfaces on our computers and phones, to stunningly realistic video games, to the seamless CGI and blockbuster movies, it's truly transformative.
Indeed. Key concepts underpinning modern graphics include the rasterization pipeline, the sequence of steps GPUs typically use to efficiently convert 3D models into the 2D grid of pixels we see on screen, applying colors, textures, and lighting effects along the way. Ray tracing, as mentioned, simulates the physics of light more accurately for breathtaking realism, long used in movies, and now increasingly feasible in real time for high-end games. Underlying all this is deep mathematics, particularly linear algebra for representing 3D transformations, rotations, translations, scaling, using matrices, and specialized data structures like octrees or BSP trees for spatial partitioning to speed up searching for object intersections. Modern graphics even allows programmers to write custom visual effects code that runs directly on the GPU using specialized shading languages like GLSL or HLSL.
And then there's the other side of the coin, human-computer interaction, or HCI. This sounds like it focuses less on generating the visuals and more on making the entire system usable, intuitive, and maybe even delightful for the human user.
Precisely. HCI is a multidisciplinary field that truly bridges computer science with psychology, cognitive science, sociology, and design. It studies how people interact with computers and designs technologies that are effective, efficient, safe, and satisfying to use. A major, perhaps the most impactful development driven by HCI research was the Graphical User Interface, GUI.
Replacing those cryptic command lines with windows, icons, menus, pointers, WIM.
Exactly, the WIM interface. This replaced complex, arcane text commands, which required significant expertise, with familiar visual metaphors that users could directly manipulate using a pointing device like a mouse. This revolutionary idea was pioneered largely at Xerox PARC, Palo Alto Research Center, in the 1970s by researchers like Alan Kay, who envisioned the Dynabook, a personal portable computer, building on earlier visionary work by Doug Engelbart.
And Engelbart's 1968 Mother of All Demos sounds legendary. It showcased things years, even decades, before they became common.
It was an absolutely stunning visionary demonstration. In a single live presentation, Engelbart showcased the first computer mouse, hypertext, clickable links, the foundation of the web, shared screen collaboration, and a windowed interface. It truly set the stage for modern interactive computing. The GUI concept was later famously commercialized and popularized by the Apple Lisa and especially the Apple Macintosh in 1984, making computers accessible to a much wider audience. Other innovations like point-and-click navigation, Wi-Sci Wei-Ji, what you see is what you get, editors where the screen matches the printout, and later multi-touch interfaces like pinch-to-zoom on smartphones are all HCI innovations that fundamentally changed how we interact with digital information, making it feel more direct and intuitive.
So HCI isn't just about making things look pretty or adding cool features. It's grounded in deep usability principles and understanding human capabilities.
Yes, exactly. It emphasizes principles like user-centered design, designing for the user's needs and context, not just for the technology. Iterative prototyping and evaluation, building mock-ups or prototypes, testing them with real users, and refining the design based on feedback. And considering human factors, like human perception, memory limitations, cognitive load, motor skills. For example, understanding that consistent visual feedback, a cursor changing shape to indicate an action, or a button looking pressed when clicked, is crucial to let the user know what's happening. Or realizing that consistency in interface design across different applications allows users to transfer their knowledge and skills, dramatically reducing learning curves. Closely related fields include user experience, UX design, which takes a holistic view of the user's entire journey with a product or service, and information visualization, which focuses specifically on developing effective ways to represent complex data visually and intuitively through charts, graphs, dashboards, and interactive visual tools.
And these fields, graphics, and HCI are clearly at the core of so many modern applications and future directions, from our phones to gaming to virtual reality.
They are absolutely central. Modern video games push the boundaries of real-time graphics and interactive storytelling. Professional simulations rely on accurate visualization. Augmented reality, AR, which overlays digital information onto the real world, think Pokemon Go or AR glasses, and virtual reality, VR, which immerses users completely in a simulated environment, are seen by many as a potential next major computing platform or the metaverse. Voice assistants rely heavily on NLP and HCI principles for natural interaction. Even experimental brain-computer interfaces, BCIs, fall under the umbrella of exploring new interaction modalities. The profound insight here is that computers shouldn't be opaque black boxes that force users to adapt to them. Instead, they need to communicate effectively via our senses, especially vision, and adapt to our natural ways of perceiving, thinking, and interacting, making them far more powerful and seamless extensions of our own cognitive and physical abilities. Key figures like Sutherland, Engelbart, Kay, and Don Norman, known for his work on usability and design thinking, really drove this human-centered perspective.
Okay. As computers became incredibly powerful, deeply interconnected, increasingly intelligent, and visually interactive, a new, absolutely fundamental challenge arose. How do we protect these systems and the vast amounts of sensitive information they hold from unauthorized access, malicious actors, and disruption? This brings us to the critical and constantly evolving fields of computer security and cryptography. This sounds like a constant, high-stakes battle against adversaries in the digital realm.
It truly is. It's an ongoing arms race. The core ideas here revolve around confidentiality, keeping secret secret, integrity, preventing unauthorized modification, availability, ensuring systems are accessible when needed, authentication, verifying identity, and non-repudiation, proving an action took place. We need ways to establish and verify trust in digital interactions and design entire systems to withstand sophisticated attacks. Cryptography, the science of secret communication, which has roots going back millennia, found new life and mathematical rigor in computer science. Classical methods like simple substitution ciphers were easily broken, but modern cryptography, grounded in computational complexity theory and mathematics, provides incredibly powerful tools for securing data in the digital age.
And the landmark idea here, the one that enabled secure communication over insecure networks like the internet, was public key cryptography. This concept still feels somewhat magical or counterintuitive to many people.
It was a truly revolutionary conceptual leap, a paradigm shift. Invented independently in the mid-1970s by Whitfield Diffie and Martin Hellman at Stanford, and slightly earlier, but kept secret, by researchers at GCHQ, the UK's intelligence agency, public key cryptography introduced a completely new way of thinking about keys. Instead of a single secret key shared by both parties, it uses a mathematically linked pair of keys. A public key, which can be openly shared with anyone without compromising security, and a private key, which must be kept absolutely secret by its owner.
That sounds almost paradoxical. How does that work? Data encrypted with one key can only be decrypted with the other.
Exactly. If Alice wants to send a secure message to Bob, she encrypts it using Bob's public key. Only Bob, with his corresponding private key, can decrypt and read the message. Anyone intercepting it, even if they have Bob's public key, cannot decrypt it. This elegantly solved a massive practical problem: how two parties could establish a secure encrypted channel over an insecure network, like the early internet, without ever needing to physically meet beforehand or use a trusted courier to share a secret key. Before public key crypto, secure key exchange was the Achilles heel.
And it also enabled digital signatures, right? Proving who sent something.
Yes, that's the other killer application. If Alice wants to sign a message to prove it came from her and hasn't been tampered with, she uses her private key to create a digital signature based on the message content. Anyone can then use Alice's public key to verify that the signature is valid and corresponds to that specific message and Alice's private key. It provides both authentication and integrity. Building on these public key concepts, the RSA encryption algorithm was developed shortly after, in 1977, by Ron Rivest, Adi Shamir, and Leonard Adelman at MIT. Its security relies on the presumed mathematical difficulty of factoring very large numbers that are the product of two large primes.
And RSA and similar public key technologies, like those based on elliptic curves, are the absolute backbone of secure online communication today. That padlock icon you see in your web browser indicating an HTTPS connection. That's public key crypto in action.
They absolutely are. RSA and elliptic curve cryptography, ECC, are the fundamental building blocks for secure communication protocols, like SSL/TLS, Secure Sockets Layer Transport Layer Security, which secures HTTPS websites, online banking, secure email, like PGP or SMME, virtual private networks, VPNs, and countless other online interactions where confidentiality and authenticity are critical.
What other cryptographic tools and concepts are there that are crucial for security beyond basic encryption and signatures?
Oh, there's a whole toolbox. Beyond encryption for confidentiality and signatures for authentication and integrity, we use cryptographic hash functions. These take an input message of any size and produce a fixed size, unique fingerprint or hash value. It's computationally infeasible to find two different messages that produce the same hash, or to find the original message given only the hash. Hashes are used everywhere for verifying data integrity, for example, checking file downloads, storing passwords securely, and in blockchain technologies. We also have message authentication codes, MACs, which combine a secret key with a hash function to provide both integrity and authentication simultaneously. And there are even more exotic yet incredibly powerful and increasingly practical ideas like zero-knowledge proofs.
Zero knowledge. How can you prove something without revealing anything?
It sounds paradoxical, but it's mathematically possible. A zero-knowledge proof allows one party, the prover, to convince another party, the verifier, that a statement is true, without revealing any information beyond the truth of the statement itself. For example, proving you know a password without revealing the password. These are becoming critical for privacy-preserving authentication and in some cryptocurrency applications. Another fascinating area is secure multi-party computation, MPC, where multiple parties can collectively compute a function over their combined private inputs, for example, calculating the average salary of a group, without ever revealing their individual inputs to each other. Again, seemingly impossible, but achievable through clever cryptographic protocols.
Wow. Okay, so beyond the specific cryptographic tools, there's the broader field of computer security protecting entire systems, networks, and data from attacks.
Yes, cryptography provides the fundamental building blocks. But computer security is about designing, building, and operating entire systems to be resilient against malicious actors. This is a huge and complex area. It includes protecting software from vulnerabilities and exploits, bugs like buffer overflows, SQL injection attacks, cross-site scripting through secure coding practices, vulnerability scanning, and defensive techniques. It covers operating system security with robust user authentication mechanisms, passwords, biometrics, multi-factor authentication, fine-grained permission models who can access what files or resources, and techniques like sandboxing to isolate potentially risky programs. Network security involves deploying firewalls to control network traffic, intrusion detection and prevention systems, IDPS, to spot and block malicious activity and secure network protocols. And of course, dealing with the ever-evolving threat of malware, malicious software. The concept of a self-replicating computer program, a virus, was actually theorized by John von Neumann back in the 1940s. Early versions appeared in the wild by the 1970s. Since then, we've seen an explosion of malware in all its forms. Viruses, worms, which self-propagate across networks, Trojan horses, disguised as legitimate software, ransomware, which encrypts data and demands payment, spyware, botnets. This has led to the development of an entire multi-billion-dollar cybersecurity industry focused on prevention, detection, and response.
So it's really about building layers of defense, assuming that some attacks will inevitably get through, and trying to contain the damage. Defense in depth.
Exactly, that's a fundamental principle. Security by design. You assume the worst, anticipate potential attacks, and design multiple layers of defense so that if one layer fails, others might still hold. Cryptographic protocols themselves are designed with formal mathematical proofs of security, often based on well-studied hardness assumptions, like RSA security relying on the difficulty of factoring large numbers. You want the security to rest on solid mathematical ground. But we absolutely cannot forget the human element. User authentication has evolved from simple, often weak passwords to much stronger multi-factor authentication. Yet social engineering, manipulating people through deception to trick them into revealing information or granting access, remains a highly effective attack vector that technical measures alone often can't fully prevent. Security awareness training is crucial.
And a more recent, truly impactful big idea that intersects security, cryptography, and distributed systems is blockchain and the concept of decentralized trust. This has gained so much attention, mostly because of cryptocurrencies like Bitcoin.
Yes, blockchain technology, first implemented in Bitcoin by the pseudonymous Satoshi Nakamoto in 2008, introduced a novel way to achieve distributed consensus and maintain a tamper-evident ledger of transactions without relying on any central trusted authority like a bank or government. This was a groundbreaking application of existing cryptographic and distributed systems concepts. The core idea combines several elements: a distributed ledger, the blockchain itself, where transactions are grouped into blocks linked cryptographically in a chain, public key cryptography for signing transactions, a peer-to-peer network to broadcast transactions in blocks, and critically, a consensus algorithm.
Like Bitcoin's proof of work.
It's exactly. Bitcoin's proof of work, PW consensus algorithm, requires participants, miners, to solve a computationally difficult puzzle to validate transactions and add a new block to the chain. This process is expensive in terms of energy and computation. The key insight is that the combination of cryptographic hashing, linking blocks, and the economic incentives and computational difficulty of the consensus algorithm makes it practically infeasible for an attacker to go back and rewrite the history of the blockchain without controlling an overwhelming majority of the network's computing power. This allows everyone on the network to agree on the state of the ledger without needing to trust any single intermediary.
So it's a powerful combination of computer science concepts, cryptography, distributed systems, game theory, all working together to create trust in a trustless environment.
Precisely. It brings together cryptographic hashing, digital signatures, distributed consensus algorithms, and fault tolerance in a novel and powerful way. And the potential applications go far beyond just cryptocurrencies. We're seeing exploration in areas like decentralized finance, DeFi, aiming to recreate traditional financial services like lending, borrowing, and exchanges without central intermediaries, using smart contracts. Smart contracts are essentially self-executing programs stored on the blockchain that run automatically when certain conditions are met. They enable decentralized applications, DApps, and new forms of organization like DAOs, decentralized autonomous organizations, which are governed by code and token holder votes rather than traditional hierarchical management. In short, security and cryptography are not just about defense. They are fundamental enablers for digital trust and interaction, constantly evolving to address new threats and unlock new possibilities like decentralized systems. Key contributors range from Shannon in information theory, to Diffie and Hellman and the RSA team for public key crypto, to Phil Zimmerman for popularizing strong encryption with PGP, to the anonymous Satoshi Nakamoto for blockchain. It's a field built on deep mathematical and algorithmic insights, locked in a perpetual struggle to enable computing's immense capabilities without opening up critical vulnerabilities. Okay, finally, as we push the boundaries of what computers can do, we're not just making them smarter or more secure in isolation. We're fundamentally rethinking how we achieve immense computational power and tackle ever larger problems, often by distributing the work across many processors or machines, and even looking beyond traditional silicon-based computing. This takes us to the cutting edge, to parallel, distributed, and cloud computing, and a glimpse into the future.
Right.
This brings us to parallel, distributed, and cloud computing. The crucial insight here seems to be that we hit limits with making single processors faster and faster, so the focus shifted to achieving more computing power by using multiple processors working together in parallel. That's a fundamental shift in computer architecture and programming that really took hold around the mid-2000s. For decades, Moore's Law gave us faster single processors almost for free. But eventually, engineers hit physical limits related to heat dissipation and power consumption known as the power wall and the end of Dennard scaling. We couldn't just keep increasing CPU clock speeds indefinitely. This marked the end of easy performance gains from faster single cores and ushered in the era of explicitly parallel computing becoming mainstream. Multi-core processors became standard in almost every device, from your laptop and smartphone up to the largest supercomputers and data centers. The challenge shifted from the hardware architects providing free speedups to the software developers needing to explicitly parallelize their code to take advantage of multiple cores.
So parallelism isn't just one monolithic thing. There are different forms or ways to make things run in parallel.
Yes, exactly. We often categorize parallelism in a few key ways. Data parallelism involves applying the same operation simultaneously to many different pieces of data. Think of processing pixels in an image, or the kind of massive vector operations that GPUs excel at. This is often associated with the SIMD, single instruction, multiple data model. Task parallelism involves having different threads or processes perform different, independent tasks concurrently, perhaps collaborating towards a larger goal. Think of a web server handling multiple client requests simultaneously. And pipeline parallelism is like an assembly line, where a task is broken down into sequential stages, and different data items are processed by different stages simultaneously as they flow through the pipeline. Modern CPUs use pipelining extensively internally. A critical theoretical concept related to parallel speedup is Amdahl's law. It states that the maximum speedup you can achieve by parallelizing a program is limited by the portion of the program that must remain sequential.
So if even 10% of your code can't be parallelized, you can never get more than a 10x speedup no matter how many processors you throw at it.
Exactly. It underscores the crucial importance of minimizing sequential bottlenecks because they will ultimately limit your scalability.
And parallel programming itself brings significant new challenges for developers, right? It's not as simple as just writing sequential code. You have to worry about coordinating tasks, avoiding conflicts when multiple threads access shared data, load balancing. It sounds like trying to manage a very fast, very complex symphony orchestra.
That's an excellent analogy. Managing concurrency safely and efficiently is hard. These challenges led to the development of new programming models, libraries, and languages specifically for parallel programming, like OpenMP for shared memory parallelism, MPI, message passing interface for distributed memory parallelism across clusters, and paradigms like MapReduce, which we'll discuss. Computer architects also had to develop sophisticated mechanisms like cache coherence protocols to ensure that multiple processor cores see a consistent view of shared memory, even though they each have their own private caches. And they designed specialized parallel architectures like vector processors, massively parallel GPUs, and more recently, specialized accelerators like Google's Tensor Processing Units, TPUs, optimized specifically for the demands of AI workloads.
And distributed computing takes this parallelism concept even further, not just across cores on a chip, but across entirely separate machines connected by a network. This is the foundation of the internet as we experience it, with clients and servers.
Correct. While parallel computing often deals with tightly coupled processors sharing memory within a single system, distributed computing involves coordinating separate machines, nodes, connected by a network. This introduces unique and often harder challenges. Network latency, the unavoidable delay in sending messages between machines becomes a major factor. and partial failures are the norm, not the exception. Individual machines can crash or network links can break, while the rest of the system needs to continue operating.
So concepts like fault tolerance and redundancy become absolutely critical.
Paramount. Distributed systems must be designed explicitly to handle failures gracefully. This often involves techniques like replicating data or computation across multiple nodes, detecting failures, and automatically recovering or routing around failed components. The CAP theorem, which we touched on in the context of databases, is a fundamental principle governing the trade-offs between consistency, availability, and partition tolerance, specifically in these large-scale distributed systems. You have to make conscious design choices about which guarantees are most important for your specific application when facing network partitions.
And these ideas of distributed computing enable truly massive, globally scaled systems that serve billions of users.
They absolutely do. Distributed computing principles underpin the World Wide Web itself, with its vast network of clients and servers, content delivery networks, CDNs, that cache content closer to users around the globe for faster access, peer-to-peer networks like BitTorrent for file sharing, and the immense infrastructure behind large search engines, social networks, and online services, which often rely on coordinating thousands, even millions of servers spread across multiple data centers worldwide.
And cloud computing is essentially taking all these concepts of distributed computing infrastructure and offering it as a utility on demand. That feels like a massive business and technological shift.
Exactly. Cloud computing, pioneered and dominated by companies like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, represents a fundamental shift in how computing resources are provisioned and consumed. Instead of organizations buying, owning, and managing their own physical servers and data centers, which is expensive and requires significant expertise, they can rent computing power, storage, networking, databases, and higher-level services on demand, paying only for what they use, often scaling resources up or down almost instantly.
The computing as a utility model, like electricity?
Precisely. The core idea is shifting from capital expenditure, buying hardware, to operational expenditure, paying for services. This lowered the barrier to entry dramatically for startups and small organizations, allowing them to leverage the immense scale and sophistication of the cloud provider's infrastructure without massive upfront investment. It fueled the explosion of web services, mobile apps, and scalable online businesses over the past 15 years.
And technologies like virtualization and containerization were key enablers for making cloud computing practical and efficient, right?
Yes, absolutely key. Virtualization allows a single powerful physical server to host many isolated virtual machines, VMs, each running its own operating system and applications, making incredibly efficient use of the underlying hardware. More recently, containerization, popularized by Docker, provides an even more lightweight form of virtualization. Containers package an application and all its dependencies together, allowing it to run consistently across different environments, from a developer's laptop to the production cloud, without the overhead of a full VM. This has become central to modern software development and deployment practices, especially for microservices architectures, where applications are composed of many small, independent containerized services that can be developed, deployed, and scaled independently.
And we also can't forget MapReduce and the Hadoop ecosystem, which you mentioned earlier.
Yeah.
That really unlocked large-scale data processing for many.
Yes. The MapReduce model, originating from Google and its open-source implementation in Apache Hadoop, provided a simplified yet powerful programming model specifically designed for processing massive data sets, terabytes or petabytes, in parallel across large clusters of commodity hardware. It abstracted away many of the complexities of distributed programming like data distribution, fault tolerance, and scheduling, allowing developers to focus on the core logic of their map and reduce functions. It became hugely influential, enabling organizations to analyze vast amounts of data for tasks like indexing the web, processing user logs, running large-scale machine learning jobs, and scientific computing, making big data processing accessible beyond just a few tech giants. So in conclusion, parallel and distributed computing culminating in the cloud model represent the dominant paradigm for achieving high performance and scalability today. They enable everything from the most powerful supercomputers solving grand scientific challenges like climate modeling or protein folding to the global internet services that billions of people rely on daily. It's all about effectively orchestrating and managing computation across potentially vast numbers of interconnected processing elements. Key figures here include supercomputer pioneers like Seymour Cray, distributed systems theorists like Leslie Lamport, known for Paxos and logical clocks, and influential computer architects like John Hennessy and David Patterson, who highlighted the end of Moore's law's easy gains and the shift towards parallelism.
Wow. Okay. The big ideas we've covered so far, from the fundamental limits defined by Turing, through algorithms, hardware, operating systems, languages, networking, databases, AI, HCI, security, and scaling up with parallel and distributed systems, have collectively built the incredible computing world we know and rely on today. But computer science, as you said, is a field that never stands still. It's constantly evolving. New frontiers are always emerging, pushing the boundaries of what's possible in truly mind-bending ways, often building on these very foundations. Let's look ahead a bit. And the first one that immediately comes to mind, the one that truly sounds like something out of science fiction but is getting real investment and making real progress, is quantum computing.
It is indeed a radical departure from classical computing, as we've known it for the past 80 years. Quantum computing leverages the bizarre and counterintuitive principles of quantum mechanics phenomena like superposition and entanglement to perform computations in a fundamentally different way. Unlike classical bits, which can only be in a state of 0 or 1, a quantum bit or qubit can exist in a superposition of both 0 and 1 simultaneously. And entanglement allows the states of multiple qubits to be linked together in a way that's much stronger than classical correlation. A measurement on one entangled qubit instantly influences the state of the others, no matter how far apart they are.
That sounds incredibly strange. How does using qubits and entanglement lead to more powerful computation?
By exploiting superposition and entanglement, a quantum computer can potentially explore a vast number of possibilities simultaneously. For certain specific types of problems, algorithms have been discovered that could offer an exponential speedup compared to the best-known classical algorithms. The most famous example is Shor's algorithm, discovered by Peter Shor in 1994. It shows that a sufficiently large, fault-tolerant quantum computer could factor large numbers exponentially faster than any classical computer. This is hugely significant because the security of widely used public key encryption systems like RSA relies on the classical difficulty of factoring.
So a working quantum computer could break much of our current internet security.
Potentially, yes. That's a major driver for research into post-quantum cryptography. New encryption methods believed to be resistant to quantum attacks. Another important quantum algorithm is Grover's algorithm, which offers a quadratic speedup for searching unstructured databases. Now, it's important to be clear. Building stable, scalable quantum computers is incredibly challenging. Current quantum hardware is still in its relative infancy, dealing with problems like decoherence, qubits losing their fragile quantum state due to environmental noise, and errors. And scaling up the number of reliable qubits is a massive engineering hurdle.
So it's not replacing our laptops anytime soon.
Not anytime soon, no. But governments and major tech companies are investing heavily in research, and progress is steady. If realized, scalable quantum computing could revolutionize not just cryptography, but also fields like materials, science, simulating molecules for drug discovery or new materials, optimization problems in logistics or finance, and fundamental scientific research. It represents a completely new paradigm of computation.
And artificial intelligence, which we just discussed as a major pillar, is itself still pushing new frontiers rapidly. What's next for AI, beyond the deep learning systems we're seeing deployed today?
AI is definitely not standing still. We're seeing several exciting directions. One major area is generative AI, which focuses on creating novel, original content, not just analyzing existing data. Models like the GPT series for generating remarkably human-like text, or DALL-E 2 and Stable Diffusion for generating complex images from text descriptions, have captured the public imagination. This ability to synthesize realistic content has huge implications, both positive and potentially negative. There's also a very strong push towards explainable AI, or interpretable machine learning. As AI systems make increasingly high-stakes decisions, for example in healthcare or finance, it's becoming critical to understand why they make those decisions, rather than just treating them as opaque black boxes. This is crucial for trust, debugging, fairness, and accountability. And the long-term ambitious goal of artificial general intelligence, AGI, achieving human-level broad cognitive abilities across a wide range of tasks rather than narrow specialization, continues to motivate fundamental research, although it remains a distant prospect. We're also seeing AI increasingly intersecting with other fields, AI for science, accelerating discovery in biology, physics, climate science, AI integrated into robotics for more adaptable physical agents, AI being deployed at the edge on smaller devices rather than just in the cloud, and continued progress in areas like reinforcement learning for complex decision-making. The future likely involves AI systems that are more data efficient, more robust, more easily explainable, and more seamlessly integrated into various aspects of our lives and work.
Then there's the Internet of Things, IoT, which feels like it's been emerging for a while but is perhaps reaching a critical mass, billions of connected devices.
The profound idea behind IoT is ubiquitous, ambient computation. It's about embedding sensing, processing, and connectivity into countless everyday objects, from smart thermostats, lighting, and appliances in our homes, to industrial sensors monitoring machinery in factories, to environmental sensors, to tiny wearables tracking our health. This creates a world where the physical environment is interwoven with digital intelligence. However, it also brings massive challenges. Security is paramount when you have billions of potentially vulnerable devices connected to the internet. Interoperability between devices from different manufacturers is a hurdle, and managing the sheer scale of data generated and the complexity of these interconnected systems is non-trivial. This is driving research into new approaches like low-power wireless communication protocols, mesh networking, edge computing, processing data closer to the source on the device or a local gateway rather than sending everything to the cloud to reduce latency and bandwidth usage, and AI algorithms optimized for resource-constrained edge devices. The promise of IoT is truly smart environments. Smart homes, smart cities, optimizing traffic flow, energy usage, public services, smart agriculture, monitoring soil conditions, optimizing irrigation, smart healthcare extending the reach of computer science deeply into the physical realm at an unprecedented scale, making our environments potentially more responsive, efficient, and data-rich.
And bridging the digital and physical worlds in a very direct, human-centric way, we have augmented reality, AR, and virtual reality, VR. These seem poised to fundamentally change how we interact with digital information and each other.
These technologies represent entirely new paradigms for human-computer interaction. VR aims to immerse the user completely in a simulated, computer-generated environment, typically using a head-mounted display that blocks out the real world. AR, on the other hand, aims to overlay digital information, graphics, or virtual objects onto the user's view of the real world, enhancing rather than replacing reality, often through smart glasses or smartphone apps. They both build heavily on decades of research in computer graphics, requiring high-resolution, low-latency rendering, and human-computer interaction, requiring intuitive 3D user interfaces, tracking user movement accurately in real time, and understanding human perceptual factors to create comfortable and believable experiences. Many tech companies are investing heavily in AR and VR, seeing them as potentially the next major computing platform after the smartphone, sometimes invoking the concept of the metaverse, persistent shared virtual spaces where people can interact, work, and play.
Whether that vision fully materializes remains to be seen, but the potential seems huge.
It does. Realizing this vision drives fundamental advances in graphics, needing extremely high frame rates, wide fields of view, and photorealistic rendering to avoid motion sickness and create presence. Computer vision for understanding the physical environment in AR and tracking user movement, network engineering for low-latency shared virtual spaces, and HCI, designing natural interaction techniques for 3D environments.
And back to the theme of decentralization, there's blockchain and decentralized tech, which seems to be evolving rapidly beyond just its initial cryptocurrency applications.
Yes. While cryptocurrencies brought blockchain to mainstream attention, the underlying concepts of distributed ledgers, consensus mechanisms, and smart contracts are influencing how we think about trust, transparency, data integrity, and coordination in distributed systems more broadly. We're seeing significant activity in decentralized finance, DeFi, which aims to recreate traditional financial services like lending, borrowing, trading, and insurance using open protocols and smart contracts on blockchains, often without relying on traditional financial intermediaries like banks. Smart contracts, as we discussed, are self-executing codes stored on a blockchain. They enable decentralized applications, DApps, that can run autonomously according to predefined rules, potentially enabling new forms of digital ownership like NFTs, non-fungible tokens, governance, and interaction. This has also led to new organizational concepts like DAOs, decentralized autonomous organizations, which attempt to govern themselves through rules encoded in smart contracts and decisions made by token holder voting, rather than traditional hierarchical management structures. Of course, significant challenges remain, particularly around scalability. Current blockchains often have limited transaction throughput, energy consumption, especially for proof-of-work systems, usability, regulation, and security. Bugs in smart contracts can be catastrophic and hard to fix. Computer science research is heavily focused on developing more efficient and scalable consensus algorithms, like various forms of proof of stake, improving privacy techniques like zero-knowledge proofs, and applying formal verification methods to ensure the correctness and security of smart contracts. It's a very active and sometimes controversial area,
but it represents a potentially profound shift towards more decentralized models of trust and coordination online.
We're even seeing truly experimental fields like biological computing and neuromorphic computing. It's like we're looking directly to nature itself for completely new ways to compute beyond silicon.
These are fascinating longer-term research directions exploring computation using radically different substrates. DNA computing, for example, leverages the incredible information density and parallelism of DNA molecules and biochemical reactions to perform computations. Leonard Adleman famously demonstrated in 1994 that he could solve a small instance of the complex traveling salesman problem using DNA strands in test tubes, showcasing its theoretical potential for massively parallel search. While still largely experimental, it hints at using biology's own mechanisms for computation. Neuromorphic computing, on the other hand, aims to build computer hardware that directly mimics the structure and function of the biological brain, often using spiking neural network architectures, where information is processed through patterns of electrical spikes, similar to biological neurons. The goal is to achieve brain-like efficiency, particularly for tasks involving pattern recognition and learning, potentially using far less energy than traditional processors for certain AI workloads. The profound idea linking these is looking to nature's own incredibly effective and efficient computers, DNA, and the brain, for inspiration to potentially overcome the limitations of conventional von Neumann-style silicon computing in the long run.
And even blurring the boundaries further, there's research into human-computer integration, like brain-computer interfaces, BCIs, directly linking mind and machine.
Yes, BCIs represent perhaps the ultimate frontier in HCI, seeking to create direct communication pathways between the human brain and computers, bypassing traditional input methods like keyboards or mice. This could potentially allow people with severe motor disabilities to control computers or prosthetic limbs using their thoughts, or perhaps enable entirely new forms of interaction for gaming, AR/VR, or cognitive enhancement in the future. It's an incredibly challenging, highly interdisciplinary area, requiring deep expertise in neuroscience, understanding brain signals, signal processing, extracting meaningful information from noisy signals, machine learning, interpreting brain patterns, and hardware engineering, developing safe and effective implants or non-invasive sensors. While still in relatively early stages, particularly for high-bandwidth communication, it hints at a future where the boundary between human cognition and digital computation could become increasingly blurred, raising profound technical and ethical questions.
And finally, amidst all this focus on increasing power and capability, there's a very practical and increasingly crucial emerging trend: green computing and sustainability. Addressing the environmental impact of all this technology.
Absolutely. As computing has become ubiquitous and data centers consume enormous amounts of electricity, a significant fraction of global consumption, the environmental footprint of the IT industry has become a major concern. Green computing focuses on designing, manufacturing, using, and disposing of computing resources in an environmentally responsible way. This includes developing more energy-efficient algorithms and software that achieve the same result with less computation, designing more energy-efficient hardware, processors, memory, storage, networking gear, powering data centers with renewable energy sources, designing systems for better thermal management to reduce cooling costs, promoting sustainable practices throughout the technology lifecycle, including responsible e-waste recycling. This connects theoretical computer science, for example, finding asymptotically more efficient algorithms that require fewer operations, directly with a pressing global practical need for environmental sustainability. Is becoming an increasingly important consideration in system design and deployment. So you can see, computer science is constantly branching out, tackling new challenges and inventing new possibilities, often by combining foundational ideas in novel ways. What's truly fascinating here when you step back and look at this whole landscape is that all these foundational concepts and big ideas in computer science, from the most abstract theory of computability right down to the engineering of sustainable data centers and the design of intuitive interfaces, they're all deeply interconnected. They form this rich, evolving tapestry, where each breakthrough, whether it's a new algorithm, a new hardware architecture, a new programming paradigm, or a new way to structure data, builds upon the last, enabling the next wave of innovation and allowing us to solve problems that were once deemed utterly impossible. Ultimately, computer science at its very heart is about rigorously exploring the boundaries of what can and cannot be automated. And then, for the things that can be automated, figuring out how to do so as efficiently, as reliably, as securely, as intelligently, and increasingly as ethically and sustainably as possible. It's a field that continuously reinvents itself, building on classic, often decades-old ideas, pushing the boundaries of the possible and remaining at the absolute core of the technological innovation that continues to reshape almost every aspect of our world.
Ah, that's a fantastic summary. So, as you, our listener, go about your day, maybe take a moment to think about this. From the fundamental limits discovered by Alan Turing decades ago, influencing what your phone can't do, to the complex algorithms sorting your search results, the layered network protocols bringing you this content, and the potential of quantum computers or AI reshaping our future. Every single interaction you have with technology today is built upon layer after layer of these profound, big ideas we've discussed. You're essentially navigating a digital landscape meticulously crafted by decades of human ingenuity and these foundational insights from computer science. So here's a final thought to leave you with, something to mull over. What new, perhaps currently obscure, big idea do you think is quietly forming right now, perhaps in a research lab or an open source project, that might be poised to reshape our digital world in the next decade or two in ways we can barely even imagine today? Thank you so much for joining us on this deep dive into the foundational concepts of computer science. We really hope this exploration has given you a clearer, more insightful view of the incredible technological world all around us. Until next time, keep diving deep.